figured some of you out there like space physics. This is the Alex Manassa. If you want to hear more about engineering and science from an engineering physicist who became an embedded microcontroller programmer engineer person, feel free to subscribe. And if you like space physics, feel free to like. All right, so I'm going to get right into it. Let me enable my desktop here. Oh, it's working today. Wonderful. Okay, space physics, space weather. That's what we're going to focus on right now, okay? Because did you know that the sun has its own weather? It has a cycle that I think is about 11 years, its solar maximum. That's when you start to see a lot of sunspots. It's when you start to see a lot of auroras. Now, what does sunspots have to do with auroras, though? How does that even happen? If I move my microphone a little closer to me, sorry about that. I'm going to explain it to you. And it has to do with the sun being a gigantic mass of plasma that also has to rotate, okay? Here, I'm going to draw you a nice red sun, okay? Now, on this nice red sun of ours, this plasma is, think of it like a liquid, but this liquid, when it moves, it generates a field, because charged particles generate magnetic fields. Also, charged particles always have an electrical field. Now, if you're a particle and you're creating a field that also affects the movement of yourself and other particles, you get very complex motion, very cool motion. The motion that you get, now the macro scale here, think of it like a liquid, just for the moment, just to get this. Because when on the sun, let's say you have all of these magnetic field lines, and all of this matter is all set, everything's straight, it's all straight down, it looks good. As you rotate the sun, remember this is a spinning ball of gas or liquid, however you want to look at it, the equator is going to pull a little more, right? And you're going to get this equator motion here because the equator is actually going faster. This thing is, it's not like Earth. It's not like Earth. Now, you know on Earth, if you have a motion and you're towards the polar region, you're just moving around a pretty small area, like around here. It's not as pronounced of a motion as this is right here, around the equator. So as you keep going, you end up getting more and more of this tangle, right? And then this tangle gets so extreme. As we tangle and tangle and tangle, you end up looking a little something like this. That's an arrow. Okay. You end up getting something that looks a little bit like this, where the tangles get so bad that you get just squiggly lines all around it. And the lines and everything, they start forming little circles. If these squiggles start getting tight enough and start getting more extreme enough, they'll start forming arcs like that. And these tangles will start to twist a little bit. They'll twist just like that. The ears are a little rough. They'll twist just like that until eventually they break off. Right? The thing about plasma is that it wants to be in a loop. The magnetic field of any object, let's say a bar magnet, you got your different polar regions here, north and south. The magnetic field of a bar magnet looks like that, right? Magnetic fields like to form closed loops. So this mass that's coming off of the sun, this green mass right here, it is going to form a closed loop. And as soon as that thing twists, let's say you start out like that, and then you keep twisting it, right? You keep twisting it just like that. Eventually you're going to get something that looks like that. Now right here, right at this point there, you can have it just break off. So you end up getting something that looks like this. That break off of matter is called a coronal mass ejection. And I've got some really cool videos to show you. This right now is a video that was taken today by a satellite showing a coronal mass ejection from the sun. It's towards the end of the video here. There it is. See? Look at that. that nice loop. I love this. You get a nice loop that comes off of the sun. And then it blows away. It can get bigger. It can that big loop can break into tiny loops just like a bubble would. Now, why on earth would that have anything to do with Aurora? It's got to load up the images here. Well, that loop right there hits the Earth, and because of the way the Earth is formed, and I'll show you this, it will hit the polar regions of the Earth. And when those charged particles hit our planet, they interact with the atmosphere, they interact with the gases. Charged particles want to be neutral. They don't want to be charged, right? They want to give an electron, they want to take an electron. Well, the thing is, anytime a molecule gives and takes an electron, it gives off a photon. All that excess energy, from the now settling down to a lower potential energy, all that excess energy goes away as a photon. Just like if I were to lose energy in a kinetic reaction, like two marbles hitting each other, there's excess energy given off in the form of a sound. It takes energy to make a sound, and it takes energy to make a photon. Excess energy escapes in some form. Now, go back to my canvas here. Boop. Hit it again, clear the canvas. Here's jolly old Earth. That's Earth. Just kidding. Don't spell Earth like that. All right, and we've got a magnetic field that looks just like a bar magnet because we've got a really cool iron core, right? Other planets like Venus do not have an iron core like we do. Ours is pretty powerful. And that iron core has been, over time, charged, I think ironically, by the sun itself. When these loops come and hit us, it'll align the magnetic field. Now, here we go. And actually, Earth's magnetic field kind of trails backwards a little bit. Here's our loop. And it has its own magnetic field. So remember that any charged particle moving through space, let's say it's a negative charge, moving through space, is going to generate a magnetic field. So you'll see this as current eddies around, like, say, an electrical wire. Now, if you start forming a big ring of these, you're going to get rings of eddies, and you almost get like a tube of magnetic field. And that tube kind of keeps this thing into a ring-like shape. As this ring-like shape moves towards Earth, it hits the magnetic field in a spectacular display. And I've got that right here, care of Goddard Space Flight Center. If you look up coronal mass ejection on Wikipedia, we're going to watch. You can see what a coronal mass ejection looks like when it hits Venus versus us. Let's go. Yeah.
What safeguards our solar system is our star.
This voice is really familiar. I don't know who that.
The sun provides a shield.
Check this out.
What safeguards our solar system is our star.
Pause. There we go. See the sun? Take a look at all these curls that are here. Look at everything has a curve to it, right? Because magnetic fields want to return. Gauss's law in Maxwell's equations, right? There's 4 Maxwell's equations. You can look them up. One of them is Gauss's law, and it's got the integral form of it shows an integral sign with a little loop around it. That means closed integral, and it says that the closed integral of any magnetic field is 0. Normal person speak, if you take a closed area, just make any circle. There's going to be just as many magnetic field lines coming in as coming out. That means there's always a closure of magnetic fields. There's always a total sum of 0. And you can see that these closures form in spectacular display. Planet Earth is smaller than some of these prominences. Prominences are these loops before they leave the sun. Once they leave the sun, they become a coronal mass ejection. See those loops?
The sun provides a shield, stretching beyond the last planet in its orbit, a force field that deflects these cosmic rays.
Mm-hmm.
But these solar winds can be dangerous too, especially during outbursts called coronal mass ejections. Want a vision of Earth gone wrong? Just look at what solar storms do to our sister planet, Venus. They strip away lighter elements in its upper
So Venus does not have as strong of a magnetic field as
oxygen,
Earth does.
And the molecule they form, water.
So getting hit with a coronal mass ejection
reaches
directly,
blue
if
from
the
Martian
ejection actually gets
including thick
past
sulfurous
those
clouds.
magnetic field lines and hits the surface, it is
Has
disastrous.
Earth avoided the
It
great
actually
fate
starts
of
changing
Venus?
the chemical composition of the
We
planet.
can see the answer as the solar storm
Now here's Earth,
approaches Earth.
okay? See how the particles move around Earth?
Our planet has a protective shield all its own. A powerful magnetic field generated deep within its core.
There we go.
In fact,
So,
that's just
I can
our
successfully
first...
pause this. Boom. All right. Sometimes spacebar works, sometimes it doesn't. I don't get it. Whatever. We have here is a simulation. So it was starting to show it, but I like this video a lot better. I like this video much better because it actually shows the field lines. And it uses technical words like magnetopause and things like that, right?
In this visualization, Earth's magnetic field structure is represented by lines that
This is Goddard
correspond to the
Space Flight Center.
paths charged particles would travel close to the Earth. The Sun's magnetic field, carried in the plasma of the solar wind, flows continuously by the Earth, distorting the planet's field and pulling it back into a windsock-type structure. The red illustrates the higher density plasma which forms the magnetopause, the boundary between the magnetic influence of the Sun and the Earth. The wind also forms a lower density.
Now, notice as Earth starts getting hit with more and more intense solar winds, you'll start to see the magnetic field. Actually, it's on this side for you guys. The magnetic field of Earth will start to shrink in and get stressed. Now, look at the top and bottom of Earth here. See how the field lines go directly into the polar regions? We're starting to find an answer to our question that we started with. What do sunspots have to do with auroras? Now, the answer is, and I'm just going to outright say it, is that the matter that gets ejected from the sun, right, that comes out, flies through space, and hits Earth will follow these field lines. I failed to mention before that those prominences, the areas where they come out of the sun, the little spots where they come out of the sun, those are where the sunspots are. So more sunspots means more prominences mean more coronal mass ejections. It's the tangling.
Magnetotail behind the Earth, represented by blue in this computer model. This process is happening all the time as the solar wind is constantly flowing by the Earth.
See the shells
But
getting
a
peeled
coronal mass
peeled
ejection,
away?
or CME, can change things.
So here's a
The
serious
higher density
CME coming
plasma
in.
and stronger magnetic field carried within the CME strikes Earth's field and significantly alters the structure.
All right, see this red zone here where it's very extreme? Also see the magnetopause. This is where Earth's magnetic field ends up equaling out to the sun's magnetic field. That means Earth and the sun kind of have equal influence over that region. That's kind of where the magnetosphere sort of ends, right? That area, if there's a satellite within that region, the satellite will be hit with coronal mass ejection. That means super high energy charged particles are going to just slam into it. And you can actually see that if, let me just go back a bunch. Oh, never mind, go here. This is a satellite view right here where I started with. Look at these little sprites and bits here, right? Those are actual charged particles hitting the camera. Those are actual particles from the sun slamming into the camera, and they create this bright spot and they create a streak because they're hitting at an angle, or they've moved it in some way.
Structure.
Now here's a big coronal
Here
mass
we see
ejection.
the dramatic changes in Earth's magnetic field and the shape of the magnetopause as the CME passes Earth. But close to Earth, the magnetic field is largely unchanged. Earth is protected from the intense solar event. This is the case for a rather ordinary CME. In this example, a CME launched by an X3 flare from December 2006. But what would happen in the case of a more intense event, such as the Carrington event of 1859?
1859, I believe the CME event was so big that it knocked down telegraph routes. Look at this. Look at how bad this is. And look at how close it is to Earth. If this gets to, I don't know what the scale is here, but if the magnetosphere recedes and the satellites that we have that control our communications and our GPS around Earth, if they're in this region, they have to turn themselves off before the CME arrives. That level of charged particles destroys electronics if the electronics are working. It's like you have to unplug everything before the CME arrives. That's why that sort of blue camera I was showing you that showed the coronal mass ejection, that one at NASA, is actually monitoring the weather of the sun to give Earth a warning of when to shut down satellites.
With the aid of similar computer models as before,
yeah, if this hit Earth
we
right
can
now,
explore some of these possibilities.
We would lose tons of
Here,
communications.
A much
like,
stronger
look at this.
CME
It almost strips it away. It's almost worrying the level.
And generates more density.
However, the auroras were probably
represented
spectacular.
by darker red. The front of the magnetopause is pushed much closer to the Earth than usual. Even the field and plasma trailing behind the Earth are more strongly distorted.
Thank you, Goddard. Who knew so much about space weather could affect Earth weather, right? The deposit of charged particles into our polar regions is responsible for the auroras. The auroras, or those charged particles that come to Earth, are responsible because of weather on the sun. Did you know that the sun ejects Earth loads and Earth loads of worth of matter into the space, into free space every day? It's incredible. The amount of matter the sun loses on a daily basis is a testament to how much matter the sun has in the first place. To lose it and then not even shrug it. It doesn't even really factor in. It's incredible. All right, guys, this has been the Alex Manassa. I hope you've enjoyed it. I filmed this earlier, and the footage got destroyed, so I'm looking a little different. I'm wearing my engineer's uniform of plaid. I hope you appreciate it, and I hope you guys have a great day. Keep on learning, keep on building, keep on making, and keep on earning. Have a great day. Bye.